Okay, so we already find out the reaction force at A will be 30 kips go up. At B will be 42 kips go up here. So now the next thing we are going to do is trying to do a cut so that we can write down the shear moment function. However, the thing is we don't know where we are going to do the cut, so which means we are going to do a random cut location. And from the A location to your cut, we are going to say the cutting distance will be X. So now what we are going to do is try to take a look which side you want to pick as your FBD. So I always recommend you to use your calculator or your blaster card to help you make a decision. You can see this is what you see from this side. It's a trapezoid. You can see from this side it's still going to be a trapezoid. So what I am going to do, I am going to choose left hand side as my FBD. So which means I am going to draw the FBD. So we can see we had reaction force 30K go up at A. And what is the distance? What is the length for the FBD you draw? It's going to be X. At the cutting location, you are going to release some internal force. So we are going to have shear force, normal force, and bending moment. However, for this problem, we don't have horizontal load. So which means we are going to have shear force. And we put X here means it will be at X cutting location. And then we are going to have bending moment, Mx here. What else we see from the picture? We still had a little trapezoid. Did you see that? Again, what we are going to do is try to simplify the load into the familiar shape, which means we are going to cut it as a rectangular and a triangle again. And we know for the rectangle, it will be acting at the center of the rectangle. And we can see from the picture the magnitude, the height for the rectangle is 2 kips per feet, right? So now, what is the simplified load here? How much is that? It will be the area of the rectangle. So it will be 2 multiply X. So now let's go to the triangle. By the way, I forgot. Don't forget to mark the dimension of the force you just simplified. So that will be half of the X. Okay, so now what we are going to do is try to simplify the triangle distributed load. And again, it will be acting on the 2/3, the centroid of the triangle. And the distance here is going to be 2/3 of the base. So now, how much is our load? It will be the area of the triangle, 1/2 base X in the height. So what is the height? So how we are going to find it? We go back to the triangle here. We have to find out the height here, which means we are going to use a similar triangle. Did you see that? Similar triangle to find out the question mark. So how much is that? So you can see it will be 2. So we had the base. Let me draw it. So what we have to do is try to find out what is the length here. Then we plus 2. Then we are going to know what is the height for the cutting location here, right? So how much is that? Take a look at this small triangle and big triangle here. You can see question mark over question mark over the cutting location X is equals to this height, which will be 4 over the full length 18. So which means this little question mark here is going to be 4 over 18 multiply X. And then we still had the base. We have to add it down. So now let's take a look how we are going to simplify the triangle load. Will be 1 over 2. The base will be X. And multiply the height. So the height will be 4 over 18 multiply X. And that's going to be our triangle load. So now everything is ready. We had all the dimension here, so which means we can try to use our equilibrium equation to help us find out the shear function and the moment function. So firstly, let's try to summarize the force in the y direction. So we are going to have 30 go up. And then we had the load 2x going down, which is the rectangle load. And we also had a triangle load going down, and the shear function we have to find. So now you can see in this equation we only had one unknown force, so we combine every term here. Finally we get shear function will be plus 30. So after we find the shear function, we can try to use moment equilibrium equation to find out the moment function. So here I highly recommend you to summarize the moment at the cutting location here, so that even if you made a mistake on the shear function, it's not going to be carried on to the moment function. So let's try to summarize moment around the cutting location. So we are going to have 30 multiply X, and then we had rectangle load multiply X over 2. And we had a triangle. It's going to be 1 over 2x, 4 over 18x here. So I highly recommend you to do one more thing. Try to mark this is the force to remind you we still need to multiply a distance. Otherwise, it's not calculate moment. And then plus moment function equals to 0. So we can try to figure out the moment function. If we combine everything here, this is your shear moment function. However, before we move to drawing the shear moment diagram, there is another way to check all your calculation. You can see your function becomes more and more complicated. Did I missing any term, or did I do any calculation correct? So here is a way to check your answer. Always remember the relationship between the moment and shear is if you take the first derivative of the moment function, you should be able to get the shear function. So try to do the first derivative of your answer from your moment function to see if you had the same function of the shear. Then if everything looks good, then you were okay. You can move on.